Track and compare LLM experiments like a pro. By the end, you will have a tiny Python experiment tracker you can run locally. You will log runs, measure deterministic latency, pick the best run by correctness and speed, simulate a simple cache-to-cut latency, and print a compact baseline summary. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced in simple Python. Experiment tracking for LLM systems is about taming many prompt runs and choices. You run dozens or hundreds of prompts with different prompts, models, and seeds. Without tracking, you lose which change actually improved accuracy or reduced cost. Success looks like repeatable decisions, a clear best candidate, and meaningful speed numbers so you know when a tweak costs more than it buys. A realistic scale here is tens to a few thousand runs, where latency and simple summaries make decisions practical. At a high level, the idea is simple. For each LLM call, we record what we asked, what the model returned, and whether the answer was correct. We add a measured latency for that call. Then we compare runs first by whether they were correct, and then by how fast they were. Finally, we test a caching trick that deduplicates repeated prompts so we can estimate real-world gains. That is our mini workflow, and it keeps evaluation focused and reproducible. Now we will log a single experiment run. This snippet creates a small, inspectable record for one LLM run. It stores the prompt text, the model response, the ground truth label, a correctness flag, a timestamp, and a run identifier or tag so you can filter later. The record is structured as a compact dictionary so you can append it to a list or write a short JSON line. The point is traceability. If you add metadata like model name or random seed, you improve later comparisons. If you add many large fields, you increase storage and search cost, but you gain more context for debugging and audits. Next, we add a simple latency measurement. This snippet measures and attaches a deterministic latency metric to the same run record. It wraps the LLM call with a precise timer and stores the elapsed milliseconds in the record. If the snippet uses repeated calls to get a stable number, then the number of repeats is an adjustable parameter. Increasing repeats reduces measurement noise but increases total runtime. You can also simulate deterministic latency when you want reproducible benchmarks without network variability. The key is a stable, comparable metric you can average, median, or percentile across runs. Now we pick a best run based on quality and speed. This snippet filters the logged runs to find the best candidate by correctness first and latency second. It selects runs that pass the correctness check and then sorts them by measured latency to pick the fastest correct run. If no run is correct, the snippet can fall back to highest confidence or lowest latency, depending on how you configure it. An adjustable preference parameter can change whether you accept a small drop in accuracy for a large speed gain. Tuning that trade-off moves the decision boundary between quality and throughput depending on your application needs. Next, we simulate caching to reduce repeated latency. This snippet deduplicates runs by prompt to simulate a simple cache, and then computes the total effective latency after deduplication. It groups identical prompts, assumes a cached hit costs far less than a fresh LLM call, and sums the unique call latencies rather than naive totals. The dedupe granularity can be adjusted from exact string matching to a looser fuzzy matching threshold. Tight exact matching is safe, but misses near duplicates. Looser matching can cut latency more, but risks reusing an answer that was specific to a different context or seed. So check accuracy after caching. Finally, we create a compact baseline summary. This snippet aggregates the logged runs into a short baseline report showing overall accuracy, mean latency, and 1 or 2 latency percentiles. It can group results by model name or tag and print a one-line summary per group so you can compare at a glance. The metrics you choose are adjustable. Using mean latency is simple but sensitive to outliers. Using median or 95th percentile gives a more robust picture of typical and worst-case behavior. A compact baseline makes it quicker to spot regressions when you change prompts or models. Recap: this is a simple, local experiment tracker that logs runs, measures deterministic latency, and lets you pick the best correct and fastest run. Use it when you run many prompts and need reproducible comparisons, or when latency is a deciding factor alongside accuracy. One caveat: simulated caching and fuzzy dedupe can reduce measured latency, but may mask context-specific correctness issues, so validate accuracy after caching. Next step: tune your cache dedupe threshold and measure the trade-off between accuracy and total latency across a larger validation set. If practical AI engineering helps you, subscribe and watch the AI engineering videos.